Okay, hi, thanks. My name is Ryan. I work for Elasticsearch, as you said. I'm also an Apache Lucene committer. And so I'm going to be talking about a lot of the different ways that compression techniques are used within Lucene to make indexes smaller. So first of all, to talk about compression, we need to kind of understand what's in an index. So we start out with documents, right? So you're going to take a bunch of documents. Here we have a document that is Berlin Buzzwords, and this is the year 2015, and we have like a unique identifier for it, bbuzz 2015. And now we want to index that. So first thing we're going to do is we're going to generate these posting lists. Probably familiar with these. Essentially, it's inverting the terms. So we're going to, for each term that exists in all the documents, we're going to keep a list of which documents contain that term. Right? And then we're also going to have something doc values. This is something Uwe talked about earlier. And this is just the inverted lookup there. So it's from a document, I want to look up for a field, what value did this originally have when I indexed it. And then we also have this stored fields, which is just like I have a string that I want to keep with my document, like the original value of the field, for instance, so I can get it back out later. And this isn't everything that's in like a Lucene index, but it's kind of general gist. So to understand compression, we first, what we're going to do is go through an example query. So when we're running a query, we're going to have to decompress some things. And so let's go through this query part, right? So we pass a query through, we're going to get documents back. What does that look like? So first of all, we need to find the terms, right? So our query is going to be Berlin Buzzwords, and so we need to find what documents contain the word Berlin and what documents contain the word Buzzwords. So first, we got to remember back to an FST. I'm not going to explain how an FST works here, but in general, it is a structure that is going to allow very quickly iterating through and getting a match. And the T part transforms, it's going to spit something back out. And so that's something we're going to use to find some information in the index. So the way that looks is we have this thing called a prefix FST. It's called a block terms reader in Lucene. The idea is that we have an FST with prefixes of our terms, and the output, when we get to the end of when we find a prefix that matched in there, is going to be the block within this terms blocks where that term actually exists, or where it should exist. And so we can traverse the FST, and the output is going to be this offset into the file, and now we get to these suffixes, right, that are going to be tacked on to the prefix that we matched. So now if we zoom in on this one block, so we looked for 2015, for instance. We went through, we got to the block, and now we have 5 there, right? So we matched 201, we have 5, and we see this postings. So this is, yet again, another offset that we're going to store in there, and this is the offset into the postings file, so for where we're going to find that list of document IDs. So how are we going to encode this postings number here? So for many years, since the 70s or 80s, there's been something called vint, vbyte, varint. It has a lot of different names if you look in IR textbooks. But the general idea is that we are going to take an integer and we're going to find the significant bits, right? So extra zeros that are up at the top, we don't care about those. So we want to find out the minimum number of bits that an integer is going to take, and then we're going to split it up into groups of 7 bits. And the way we're going to encode this is taking the first 7 bits and putting it into a byte, and then adding a 1 there. And that means there are more bytes to read. And so then we can keep doing this until we've run out of bits that we need to encode. And then when we're decoding, we can read through until there's no longer a 1 in that most significant bit. And then we can use bit masks and shifting to rejoin all the bits together, and we have our original integer. So let's look at some examples of that. So we start out with a very simple number, right? 1. Notice that there's a lot of zeros. These gray zeros are things that don't matter, right? So the only meaningful bits when we have this 1 byte is the 0 at the top, because that means this is the last byte, so it's just a 1 byte integer. And then we have the lower 1 bit there. Then we go to a value 253. So normally, this value would take up 8 bits, and we could store it in a single byte if we wanted, right? But in this case, because we only have 7 bits per byte, we have to spill it over to another byte. So again, we have a bunch of zeros, but if you, a bunch of wasted zeros, but if you look at the total number of relevant bits across our 16 that we have there, it's still a pretty good compression ratio. And then we get to yet another larger number. Notice here that in the 3rd byte, it looks exactly the same as that first byte that we had before. So context really matters, right? We need to start at the beginning of where the integer is, because there's no way for us to know, like, this isn't the beginning of an integer, right? So things like UTF-8, they have special values that they have in these significant bits that tell them tell a decoder where it is. So you can actually jump back to the beginning of a UTF-8 encoded sequence, but with vbyte you can't. And then finally, this number, all ones essentially, right? So we have 28 bits of ones. This is the biggest number that we can fit in 4 bytes. So if we had a larger value in this, it's actually going to take more than if we had encoded in ints. That's okay. Because we don't have very, very large numbers like that very often. So now that we've found this offset into the postings list, we're going to go try to decode our postings. So how are we going to do that? So if we have our original document IDs that we had encoded in the postings list, usually these are going to, well, first of all, they're going to be sequential, right? Because we're going to do them in order so that we can do like fast intersections, so that we can keep track as we're intersecting and know that we don't have to go back and look for a different number. But most of the time, or all the time, we're going to want to store deltas, because usually if you have a term that is very common, then the difference between the two numbers is going to be much smaller than the actual number, right? So if I have document 10,005 and document 10,006, I don't really need to store 3 bytes for each of those. I just need to store 1 byte, the difference between them. And so we can use vint, vbyte, right, for that. As we saw earlier, notice again there's a bunch of gray zeros. That means they're wasted space, right? Even though we're much better than 4-byte ints, we're still not as good as we could be. And so that leads us to how we're going to take care of very large postings lists. So this vint that I described, this was, like I said, has been around since 70s or 80s, and it's still used in Lucene, but it's used much less. And so when we have a very large postings list, we actually we want to use less than 1 byte per value to encode it. Because, for instance, if we have a lot of just 1, 2, 1, 2, 1, 2, right? These are very small numbers that we can encode in a couple bits. We don't need a whole byte to encode them. So in order to do this packed ints, we're going to go through all the values within a block that we want to encode, and we're going to find what's the minimum number of bits that is required to encode all of the values that we saw in this block. Once we do that, then we can put each of the integers into a bit field, and we know that it'll fit inside those bits, so we aren't going to have any leftover bits that don't fit. And then when we're trying to decode, because we know ahead of time how many bits, or the size of that bit field, we can use simple offset math, right? So you see here, if we just have to multiply and divide, right? And then, and again, shifts and masks similar to vbyte. It's a little bit, little different shift, right? So with vbyte, we're shifting by 7 bits. Here, we're shifting by some number n. So an example with with packed ints postings. So our original numbers, we have 1, 5, and 2. Remember, these are deltas. These were our deltas that we had in our last example for vint. So the first thing we're going to store, this number that's all in red, this is like a description. All this says is this is the number of bits per value that we're going to store. And so we have a 4 there, right, in binary. And then each integer is only going to take up 4 bytes. So notice that we are taking up the same number of bytes in this little toy example that we did with vint, but if we kept going, if we had a lot more values, obviously still that fit within those 4 bits, then we'd be able to store them more compressed than if we had vint at a slightly, potentially extra cost, right? Because we have to shift and mask a little bit more. That's what we use to decode our postings lists. And so we're going through our query, we found the terms, we found the postings lists that were associated with those terms. We did, let's say, an intersection. So we wanted to find the documents that had Berlin and buzzwords. And now we want to figure out what are the most relevant documents. What do we want to actually return to our user? And so for that, we're going to score the documents. So Lucene has this complicated scoring function. You don't have to understand anything about it. Just know that we're going to talk about this part here. So this is, these are the norms. These are an index time scoring factor that we're going to store in the index, and we're going to load or have loaded at query time available for us so that we can tack that into the score. So it's all the index time scoring factors. The main portion of it is what's called a length normalization. And what that means is if I have a match, for instance, in a title field that is very short, it's probably more relevant than if I have a match in a very long field, like a body field or something like that. And so this normalization factor is basically a weight that's going to be applied into that score that's going to boost up documents that matched in a shorter field. This value is actually an 8-bit floating point integer, or floating point value encoded as an integer. The reason for that is only big differences matter. So if I have a document that matches, or that matched in a field that was 1 million in length, and one that matched in a field that was 2 million in length, they're basically the same, right? What matters is if I have a field that matched with, that had 2, or length of 2, right, or 3 or 4. But all those 2, 3, and 4, those are also essentially the same. So we have small and large. And so we're actually going to truncate this value, essentially. It's lossy, but it doesn't matter. It's only these big differences that matter. However, the API does allow for longs, so the encoding has to support that. This is more for IR researchers and stuff like that, but by default, we use an 8-bit float. And norms right now actually have 7 different techniques. I'm going to talk about most of them. So the first one is simple. This is just an array. So remember, we have an 8-bit float, so we know that all the values are 255, or 0 to 255. And so we just store an array of the values, essentially. Next is going to be constant. This is for cases where, let's say I accidentally enabled norms for a field and I didn't mean to, and all the values they're just length 1, right? So every single of these documents is going to have the exact same norms value. And so for this edge case, we have a special encoding which just first detects that all the values are the same, and then just says, hey, this is the number of values we had, and here's that one value. Then we have, let's see, delta. So delta is like the packed ints that we saw earlier, with one additional thing. We're going to store this, this minimum value. And then once we store that minimum value, every time we decode one of these packed integers, we just add it to that minimum value. So in this case, you can see that 10 and 5 are just like we expect, but 20 normally would have taken 5 bits. But because we offset it by that minimum value, we were able to store it in just 4 bits. And so if that minimum value is large, then it can help us have a higher compression rate. The next one is going to be table compression. This is, again, going to use packed ints, except that the values that we're going to write out here, so like 0, 1, 0, 0, and 0, 1, right? So these values are actually offset, or, indexes into a table of the real values. And the reason we do this is the real values were larger, right? 10 and 5, we wouldn't have been able to fit those into the 2 bits that we encoded here. And so if we had lots of other values, but they were all the same essentially, if we just had a bunch of 10s and 5s and 10s and 5s, then we're able to encode this much more compactly by storing the values separately, and we store them sorted too. Indirect is a little bit more complicated. So the idea here is that if we have a value that's very common, but it's not the only value we see. So here we have 2 10s and a 5, right? Imagine we had tons more 10s. In fact, it's the trigger that we use is 97%. It was kind of randomly chosen, but tested. So if we see 97% of the values have one, or 97% of the documents have one value, then we'll just encode that common value. And then this indirect is going to have 2 arrays. So we start out with, first of all, the array of the doc IDs that had a value that wasn't the common value. And so here, our document 1, right, this is zero-based indexing, so our second document did not have 10. So this is the uncommon value, and so that was our first document that we encoded in our array of rare doc IDs, and then we have a corresponding array that matches it element for element with the actual value that document had. And because this first array is sorted by document ID, we're able to do binary search over it. So we first do a binary search and see does the document that we're trying to find the value for, does it exist? And if it doesn't exist, we know it's the common value. And if it does exist, then we take that index where we found it in our array of rare doc IDs, and we go over to the values array, and we look it up there. And the final one that we're going to talk about for norms is patched. So they're actually 2 patched, but they're basically the same. The idea here is to combine a couple techniques that we've already seen. So we again have common values, but this time it's multiple common values. So if we have a small number of common values, then we can again use an array of sorted values and use the index into there as an ordinal, meaning an identifier for that value. And then we reserve one special value in our bit field here. And we say that special value means it's not actually in the array. And for that special value, we're actually going to go back to a table, just like we saw. So those special values, remember, they're 3% or less of the documents are going to have them. So it's very rare that we're actually going to go to this exception table. So it's a little bit more expensive when we have to do this extra indirection. But the very, very common values are going to be faster. Now, with that scoring that we saw, sometimes we want to add some extra stuff to that score. Maybe we want to multiply by a popularity. And so every document, we're going to store this popularity. And this is where we need this way to look up for every document, every doc ID, what's the value that was associated with that when we index the document. And so that's where we get doc values. So doc values, there are a couple different types of doc values. We start with numerics. We have support for both single and multi-valued. binary, and then binary enumeration. So binary enumeration is more like the ordinals, so we have like a fixed number of values that we're going to see, and we're going to refer to them by this ordinal, this unique ID for that value. Notice that binary doesn't have multi-valued. That's because if you want to have multi-valued support for binary, you could encode whatever you want into binary, right? It's just a bunch of binary. So some of the ways that we're going to encode doc values, we've already seen a bunch of these. So delta compressed, table compressed, const. These are things that we saw before with norms. We also have prefix compression, which is very similar to what we're doing in the prefix tree, right? That prefix FST. But there are two extra techniques that are kind of a base for a bunch of the different doc values formats that we're going to talk about now. So the first one is GCD. So imagine that I have a bunch of values, and let's take a timestamp, for instance. So let's say I'm storing milliseconds since epoch, and I'm actually passing in seconds. For whatever reason, I'm passing in seconds, but I'm storing milliseconds. So that means every one of my values is going to be 1,000, or a multiple of 1,000. So what I can do is divide all of those values by this common multiple, right, the greatest common denominator, and then I can just store the greatest common denominator, or the multiple of the GCD. And if I store the GCD first, so this is the divisor here, I'm going to store that 10, and then every value is going to be just the smaller value, divided by the GCD. And so we're able to, again, use this packed ints, right? We're able to pack the bits in to as small value as we can fit. The next one is monotonic. So the idea of monotonic is we have values that each document is going to have a bigger and bigger value. And we often see that with like offsets, for instance, right? So like those offsets that we saw in postings, or to refer to the postings lists, these are going to be bigger and bigger, right? Because the first term is going to be written for the second term, is going to be written for the third term. So these values are going to grow. And what we can do is fit, in this case, a linear model is what we use, to the growth. And then we can just encode the difference from the model. And so here we can see that our first two values, right, those are the ones we fit the model to, and they fall right on it. So all we need to encode is a 0 for those. And then we have this one value 5 there. It's a little bit off, but we just need to encode a 1, right? So this is what it's going to look like. And obviously we have to encode what the model is, right? So we're going to store the M and the B, and then for each value we're able to take that, apply which document number we're on, and add the deviation from that. So finally, we have got all of the documents now that are most relevant, right? We've done a sort on this score that we took our relevancy score from Lucene, we multiplied it by popularity that we pulled from doc values, and now we want to return something to the user. So what are we going to return? So we want to look up in the stored fields API in Lucene stuff that we stored along with the document. So this could be like a unique identifier that we originally had. Maybe it's the full text of the document, like _source in Elasticsearch. And so we want to look that up. So how are we compressing that? So there's two different techniques that are used. We first have LZ4. And so LZ4 is based on LZ77. And in general, the way it works, this is not going to be very exact. But so we're going to start by writing out, we have bbuzz 2015 bbuzz. So as we're writing out, we write out bbuzz 2015. And then we get to the second bbuzz, and we notice, hey, this is the same thing that I saw earlier. So instead of writing out all of those bbuzz characters again, we're going to write out a couple bytes that actually refer back to where that bbuzz originally occurred, right? So it's a reverse offset and a length that we're going to store. And so essentially, we have two different types of entities within the encoded stream of LZ4, LZ77. We have literals, which are like, these are the things that I actually wrote out. And then we have back references, right? These things that are referring back to previous text that we found. Now, in recent versions of Lucene, we added the ability to have a higher compression ratio. And what we do this with is deflate. So deflate is very similar to LZ77, or LZ4, LZ77. It's all the same family of encodings. The idea is to take LZ77 and then do a second pass over it. And in that second pass, we're going to find these common things that are still common, and we're going to actually compress them down even more using Huffman codes. So we're going to build a dictionary, keeping track of how many times we saw particular tokens, and then we're going to rewrite it with these smaller binary values. Okay, so that is my talk. And for questions, if anyone has any questions, I have beers in honor of Robert Muir. And yeah, thank you.